exactly on two sides to him, and the donkey is here. And he has to choose, but since this one is exactly the same as that one, he can't decide. So he starves to death. Because why should I go here, why should I go here? Now that's a donkey. So the symmetry is if you can't decide which way is better, that's symmetry. And you don't want to be a donkey and get stuck. So here, it's a similar story. I have a point charge. No direction is different or better than another. And all distances on a sphere are the same distance away, right? By symmetry. So if I want to be an R, I can be an R here, it's all the same. Okay, so let me be smart. And I know that, look, there's no reason for the electric field, if I pick the same radius, there's no reason for the electric field to be different at this point than at this radius, by the donkey effect. They're all the same. E doesn't know the difference. So the magnitude of E can only depend on R. It can't depend on the angle, because there's no difference between this angle and that angle. So E is a function of R. And also, it's a constant on a sphere. So let me pick my bubble sphere as a sphere, a bubble surface. And in honor of Mr. Gauss, we call any such bubble a Gaussian surface. And it's my choice. I pick it just because I'm dealing with a point charge. I pick a sphere for my Gaussian surface. Why? Because then I know that the electric field can only depend on R at most. It can't depend on the angle, because every angle is the same. Now, it might depend on R, it might not. But at worst, it's due to that. And then I integrate. I do my integral over the whole bubble that I've chosen, a sphere, times the area of the sphere. And let me see what I get. Now, I know that E at any one particular R is going to be the same. So as I go around the sphere, R is the same. So I can take that E of R out. And I just get the integral of the area over that sphere, which I know the area of the sphere from geometry is 4 pi times R squared. Okay? All right? So now, if I know Coulomb's law, it actually tells me what E of R is. Coulomb says E of R is, well, we wrote it earlier as KQ over R squared, which we're going to rewrite. You'll see it because we want the formula to come out different. We write it as, instead of K, we put down, 4 pi epsilon naught. It's just another constant, because we're going to get, otherwise we're going to get 4 pi showing up here. Q over R squared. So if I plug that into here, I get that the integral of all the stuff coming out of that point charge, E dot dA, is equal to E of R, which is this guy, 1 over 4 pi epsilon naught, Q over R squared, times the area of the whole bubble, which is 4 pi R squared. And the reason I do that, and now you see why I put in the 4 pi here, because now it cancels, simplifies the formula to Q over epsilon naught. So that's a Gauss law for a point charge. And so if it's telling me, if I can count the lines coming out through a bubble, if I can count them, it will quantitatively tell me how much charge is inside the bubble. That's it. So that's a very nice thing to do. And the nice part is that it helps you solve some few nice problems easily, and it's just a good qualitative thing. For example, so here, these are all that I've just gone through. Yeah, but you see all this mystery about picking Gaussian spheres and all that kind of thing. All you're trying to do is capture the flux coming out of any source. And you pick the surface that's going to make it easier for you to do. So I have here that the E and the A are parallel in this case, and so it makes the integral simpler, and I just do all my stuff, and what it tells me is that the flux over the whole area tells me the charge inside. Okay, so it's useful because it depends only on the net charge inside. There could be positive charges inside, and there could be negative charge inside, but now it depends on where you draw your bubble. See, for example, we had what was called a dipole. Now, if I draw my bubble, say over here, there'll be net charge coming out, net lines coming out up to the minus, like that. And going like that. If I draw my bubble here, there'll be net lines coming out. It tells me there's a plus charge inside. If I draw my bubble over here, there are going to be net lines coming in. Tells me there's a negative charge inside. If I draw my bubble over here, there'll be lines coming in, there'll be lines going out on the other side. Tells me there's nobody inside. That's it. It's embarrassingly simple, isn't it? What's the big fuss? Okay. So now let's quickly move on. I wanted to make a few demonstrations here. Okay, now where it gets to be kind of interesting is when you can actually solve some problems which otherwise might be quite hard. For example, this one here is if I have a solid ball of charge, meaning that there's a uniform density of charge inside. I'm thinking here like a meatball of charge, solid ball. It's not a tennis ball, it's not a basketball, not a shell. And you might want to say, well, what's the electric field at this point in the ball? Now, that might be a very hard problem, because if I did it by Coulomb's law, I'd have to take every little charge in here, find the field, take this little charge here, maybe I could do something symmetrical, put it over here and find the field here, and I get an integral over the whole meatball and figuring out all the fields and this and that, the fields over here. And it's a hard problem to do it by Coulomb's law, looking at every little bit of charge. But by Gauss's law, you can do it in about 4 steps, simple steps. Because what you do, oh, by the way, we have to square them out here at 4 o'clock. It's a department meeting, so I have to be perhaps extra brief. But that's what this proof, I really won't go through it. But the point is, if you have a meatball of uniform charge, what you do is you pick your Gaussian surface, do this, and you ask to get the field at that point. You just say how much charge is until you turn it around. You say, I have the charge, now I want to find the field. That's what this is about. So what I do is I say, how much charge is inside that sphere? And then it must be that, and if I pick the sphere right at the symmetrical point, the field is the same in all directions by symmetry, because I've got a symmetrical situation. So if I know the charge inside, I can get the field times the area, and I know the area because I know this is a sphere. So I put, let's say, this distance here, little r, is 4 pi little r squared, and now I want the field at r, and this is the amount of charge inside. And if it's a uniform charge, I just multiply by the charge density times the volume. So I can turn it around and get the field in these special cases, 3 special cases that we have. We have the spherical case, we have the line case. These are the ones you could do by grinding away with Coulomb's law, but by Gauss's law, you can do it much more simply, because these things have a lot of symmetry. I'll show you my, the symmetry that you have is against the line. It's cylindrical symmetry. The lines must, by symmetry, be going outward. And they must be equal, the fields must be equal at equal distances from there, like the Donkey effect. There's no reason to choose one distance over another. Could be space dependent, but they must be perpendicular. So that's the symmetry of the line, and all you do is use your cylinder. This is the symmetry of the flat plane. The lines are coming out. And those are the cases we can solve. We can solve a point, which is my famous electric field line, who lost a cheek, actually, in the process here. But the electric field line is like that, as a point charge, spherically symmetric. So I would use spherical bubbles around here. Here I would use cylinders, and here I would use pillboxes lined up with this, so that the surface is either perpendicular or parallel. And I can pick a bubble to make my life easy. Now, how much time do we have? 5 minutes. I see Paul back there. So that means they're coming after us. Any case, one thing I did want to show you is the fact that where this has a very interesting result is that when you're dealing with electrical conductors, you can make some very powerful deductions about what's going on in an electrical conductor from the Gauss law. And that is the fact that if you draw a bubble inside a conductor, one thing we can say about the electric field inside a conductor is that it's 0. The reason being that if there were an electric field, it would apply a force on any free charge. And in an electrical conductor, there are lots of free charges. So that if there were a field and there were a charge, it would move. But we're assuming here static. We're assuming a situation where everything is settled down. We put an electric field on, and all the charges do whatever they're going to do, and they settle down. So there is no motion. There are no forces on the charges anymore. So that the only way that the forces can be 0 is if the field is 0. Everywhere inside a conductor. So we can do, let's see, we have a very important result. That's a very important result. For example, it tells us that the electric field is perpendicular to the surface. Because if you put a little box around here, there is no field inside. There may be a field outside, but there is no specific, if you have a small area, there's no reason for the field to be one direction or another. So it says that the field actually must be perpendicular to the surface, and it must be 0 inside the bulk. So remarkable things result from that. For example, if I have a cavity inside a conductor, and I even put a charge on here, because there's no field here, that means there can be no charge inside, means that the charge that was mobile inside here will go to the inside of the cavity, leaving behind charge out here. So the charge that may have been put in here shows up on the outside, but on the inside, there is no net charge, because E around this whole area of this whole bubble must be 0, because E is 0. Okay, what this ends up being is a screening effect. Namely, if I put an electric field on here, it shields the field from the outside. So I want to show you quickly here. I don't know if you can hear this. Can you hear this a little bit? It's pretty weak. Oh my goodness, it's a religious program. But all I'm going to tell you is that if I put this inside the screen, the electrical fields carrying that electrical wave will go away. So the screening here means that the electric field is stopped by this metallic screen, which is something that we use in electrical experiments. If we want to prevent electrical signals from getting into the equipment, we build a cage, something called a Faraday cage, in which the electrical signals do not get in and interfere with our instruments. Well, with that, I'm afraid we have to call it a day and let the class of professors take over. Thank you.